Good morning, everyone. This is Jim Chastain, EasyPower, and we're doing our weekly refresher episode this week on Transient Motor Start, and appreciate everyone joining us. Transient Motor Start is actually one of the more fun modules to work with. It's based on PowerFlow, and what it allows is the ability to design, optimize, and troubleshoot motor starting cases relatively quickly, be able to look at things like starting times, starting speeds, torque, voltage drops, and relay interactions, and also be able to ascertain if you're going to have a problem with contactor dropouts. It's based on the PowerFlow module, and what it allows you to do is to do successive recalculations of the PowerFlow model over time as events are taking place based upon some stimulus. So this can be starting or stopping, faulting buses, or looking at the effect on remote buses as some of these events take place. This also gives you the ability to kind of tune your starter performance, and one of the clever ways that we permit that, or the tool implements that, is with script, being able to run scripts that you've pre-selected to run a particular scenario. So with this, you can go through a series of what-if examinations and what-if cases on your own to determine things like the best torque or the optimal torque and speed as different scenarios take place and different stimulus are applied to the bus. So for those of you that have Transient Motor Start, obviously you need PowerFlow, and that's where Transient Motor Start introduces the time element, and be able to customize plots and be able to produce the results very quickly and easily. Again, it's based on the same EasyPower tool platform. That the overriding theme is the intuitive graphical user interface, which makes it a lot easier to get results quickly and not have to become a power user and use the tool every day to get productive results. So let's jump into the tool and see if we can't get some specifics going. So the first example I'm going to use, all right, so with the tool, there is installed a sample directory that, as you go to your open file icon here at the top, it goes into this directory that's been installed with the tools under Documents, EasyPower 9.71 line, and we're going to look under the sample folder at DS1 example. So this is essentially a large motor complex where we have multiple motors sitting on a 4.16 kV bus. And you can tell by looking at the one line that we've got the motors characterized. Right now I'm in Database Editor. As I go in and look at the motor characterization, or the data that's been entered, we have the specifications for a 3,000 horsepower synchronous RPM of 1,800. We've calculated the full load current load to be a 2617 kVA, so it's fairly significant as far as a load. We've calculated the short circuit X over R, so we've gone through the process of verifying that we're in good shape as far as the short circuit and arc flash. What we really want to look at today is the performance of the motor, or the reaction of the motor to stimulus, and that's the function of the stability module. So as we go to the stability tab for this particular motor, we can see that there's no data entered, and so what we want to do is actually set up, since we've already got the power factor and efficiency entered or calculated for a standard motor of this size, we're going to go into generic manufacturer selection, and we're going to pick out a standard induction model and load that in from the library. The first thing it's going to ask us is, do we want to override the power factor and efficiency that we already have? Well, the answer is no, because that's primarily what we've entered when we characterize the motor. So at this point, the tool is loaded in, if you will, average settings for a standard induction motor from the library. And what that means is all of these system parameters or motor parameters have been entered based upon those basic average values, and they may or may not match specifically what our installation is, but it gives us a starting point. So likewise, we also want to show the model for the starting leg of the motor operation. Here we're going to pick a generic standard time versus speed and load that in, and again it's got average values for those parameters, and we're bringing in the running model generic standard T versus speed. And as we do that, you'll notice the icon has changed then in the one-line diagram from the basic vanilla motor icon to something that looks like it has a rotor inside, which tells us that we have stability data there. And just because it's EasyPower and I can do this, I'm going to copy and paste this into the other motor. And as we go in and look at stability, you'll see it's carried over exactly the same information, good, bad, or indifferent. All right, so at this point, we have the ability to go in and look at some stability performance. So let's do that. I've gone to stability module, and in this case, we're working specifically transient motor start. And so you'll see that the tool launches in a state where we've solved the PowerFlow equations, and in this particular case we have one motor breaker closed, and so we have the I believe it's kilovars. I'm going to look at I want to look at PowerFlow options, and on my one-line diagram my display unit for loads is MVA and power factor. So if I want to look at MVA and MVAR, I can see that this is what the load is for quiescent operations for this particular motor. If I close this breaker, you can see that I get essentially recalculations over here, but I've also, based upon a double click of this breaker, produced an auto plot. The tool knows that this is a motor, so it's showing me the voltage applied, the current that the motor's drawing, the speed of the motor. Here we can see pretty much a linear start, and then the braking horse or the torque on the motor. And so that's literally just the result of starting this or double-clicking this breaker. As we go in, and you might say, well, how do we know what generated these particular display? That's part of the PowerFlow options. As we go in and look at PowerFlow, it's actually part of the stability options. And what we've done is set on the double-click function to open a breaker or switch, or to close a breaker or switch. We have by default a delay time of 1 second before a plot starts, and then run the simulation for 6 seconds after that particular event. So if we come back and open this breaker, you'll see we have the same plots again. This time, though, it'll be for motor M1. Okay, that's all well and good. The question is, how do we, and so that's built into the tool. So double click will exercise the breakers. It'll also fault the bus. And here we're seeing the bus voltage and bus current, and this will end up being the short circuit current for the fault. And quite interestingly, this is actually a more accurate representation than we see even during arc flash, because this is over time rather than just a snapshot at half cycle, 5 cycles, and 30 cycles. All right, so the focus of where I'm taking all this discussion is to the area of writing scripts. what we want to do is be able to see the effects of starting a motor and then maybe move that time around versus the either the existing operation of a current motor or starting, say, in a staggered mode, what the effects of both motors have on the system. So we're going to start a new script. I don't know if you kind of saw where this came from. I click on the Edit Script icon, and we're going to set a new one. And let's call this Starting Motor. And because we probably end up with two of them, we're going to call it plural. And so for starters, let's run the simulation for a second just to see that things are steady state and quiescent. So we're going to select Run for Time from the list of activities, run it for 1 second. Then we're going to, in this case, close the high voltage breaker. And it'll be for M2, BHM2. And then we're going to run this for 3 seconds. So we'll end up with a total 4-second simulation. Now, when we exercised the breaker, what we saw was an auto plot, and the tool made its own assertion of what elements to plot. And so when we're doing this through a script, we have to define our plots because there won't be an auto plot there. So let's plot in screen 1 or plot 1 our existing current, let's say through the existing motor. So we want to look at the motor current for M1. We want to look at the motor current for M2 and see, we're trying to see if there's an effect on M1 from starting M2. And then let's go ahead and look at the speed of motor 2 as it's coming up to speed. All right. So as we pick out that starting motor script and run it, you can see on plot 1 now that we see the impact on the current in motor 1. Sure enough, there's a change in the current there, and the current in M2 and the speed of M2. All right, so let's say, well, what happens if we start both motors at the same time? So we go back to our script. Let's edit a script. And instead of running for time, let's take this out of here. Let's close the breaker H for M motor 1. And now run this for some time. Say 4 seconds. Now, obviously, it won't have any effect. If we run this, we'll see that because M1 is already running, nothing's going to change in that particular side of things. So let's reset it, open this breaker, resolve, and now let's run our script. And we're looking at M1. So that's not what I was expecting to see. Let me go back and see what we got. Close breaker M2, M1. Let's try this again. Everything's kosher and steady state. We're still not showing, oh, did I put it the wrong direction? I was opening it rather than closing it. You got to be smarter than the switch you're operating. So we're going to close high voltage switch, breaker, and we're back in business. Okay, so now the next thing we want to look at is what happens if we want to change a motor parameter in the middle of one of these simulations. And the way you do this is we're going to go back to the database editor. Let's go ahead and save what we got here. And I'm going to open up a motor dialog box, and as we go to the stability field, we see that all these parameters are listed for this particular motor. And so what I've done is I've gone to the bottom of this this little 2-column spreadsheet, left-clicked, taken to the top and copied, and then pasted it into a spreadsheet like this. The reason is I want to know what the order is serially for each one of these parameters. For instance, if we wanted to manually change, or during the course of our simulation, change the power factor, or we wanted to change, let's say in this specific case, the torque, the moment of inertia. Moment of inertia here is H, it's number 23, and as we look at the value that was loaded from the standard library, we see that it starts off at 0.4. Well, what if I have some sort of clutch or some sort of mechanical device that can actually change this moment of inertia midway through the start cycle? So what I want to do is take advantage of that. So now as I go back to stability, I'm going to go into my starting motor script. And now as we get into, let's say for one of these motors we want to change its moment of inertia. Of course, this will be right at the time the motor starts, so that's all well and good. So we're going to change factor 23 or parameter 23. We're going to change it to 4.5. That wasn't where I wanted to end it. Now we need to run the simulation for, say, another 4 seconds. And let's see what we got. All right, so what we see is the effect of M1, where now we have a moment of inertia that it has to deal with. And we can see this down in our log here, where M1, we changed the motor parameter in row 23 to 4.5. And so in the simulation, we see that we changed the double cage induction motor, or parameter H, from 0.4 to 4.5. So a 10x multiplication, and consequently it's going to take it longer to get up to speed, and it actually has an effect on the operation of motor 2. In fact, it looks pretty messy. I think I got a hiccup in my let's start a new one. Let's talk about moment change. I think I had a hiccup in my change in variables downstream. All right, so we're going to start a motor. So let's run for time 1 second. Let's go ahead and close a breaker. Let's run it for a second. Let's change its moment of inertia. And then run for another 4 seconds. So the point being that you don't want to get too fancy when you're doing multiple steps, and make sure you're not getting erroneous readings. So we're just going to start one motor this time, and we still got a hiccup up here that's not surviving that much of a slam. All right, so that's, I'm kind of doing overkill on my simulation. Let's kind of back it up to where we get it under control. All right, so we're going to run for 1 second. Let's change the motor parameter. We'll get this right yet. On motor 1, it's parameter 23, and we're going to change it to 4. And then run for another 4 seconds. All right. There's a little more civil. All right, let's see what the effect is now on motor 2 if it's already online and we run this same moment change script. So there's actually an effect on motor 2, which was surprising to me, and again, one of the aspects that this tool allows you to do through a what-if scenario and be able to capitalize on a lot of possibilities that you may or may not be aware of in your system. Now, the reason for kind of going to all this trouble to show you how to change, and this works with any of the parameters in the characterization of the motor itself. So we've effectively been changing the moment of inertia, which by default started at 0.4, and we've changed it to 4.0, which is the step right here. Now, and so you can pick any of these parameters and vary it as your heart desires to see what's going to be the effect in the system. Another way to do a similar kind of a thing is to be able to change the soft start operation. And if we go back and kind of look at our database editor, we're not going to save any of this stuff. If we look at the parameters that were brought into the tool for soft start, you see this currently sets up at 100% operations for the soft start. So that may not be realistic, and it's another way to gradually increase the load on the motor. So let's, I have another one that I've actually done here that I've played with. And here we have a very large motor on a 2.3 kV bus. And what we want to do is, as we're setting up this particular stability numbers, the model, we want to space out the soft start, and we're going to start at 10%, run the soft start for 0.2 of a second. Let me go back and get this right. We start off at 10% and then scale to 45% and then go to 100% and we're going to do it in 5-second intervals. And we're going to see how the system works with that type of a profile. And we can do the same thing with a script. In this particular case, I just want to do it in a steady state start. And as we do that, we click this bus. And again, because the tool knows that it's on a motor line, we see the fan starting parameters here with the current and the kilowatts and the kilovars, and consequently this may or may not be what we want to deal with. In fact, we may want to plot some other buses. Let's see if I have anything set up. And we may want to see what the impact is on the main power bus. So let's go over there and look. Here's the fan speed and power, and here's on the main bus, and we're seeing a drop of almost 5 pu as we go through that starting profile. So that may be something that we want to modify, and we do that again with the adjustment on the soft start profile. So the ability to set up and try a what-if scenario with the script gives us a lot of versatility, and I think that's mainly what I was trying to show today, based upon, in this case, refining what our soft start time sequence will be and works best for the system. So let's see if we got any questions, if I haven't lost everybody along the way. Okay, sometimes, let's see, the question is, sometimes the motor data sheet is not available and required to make a model, the worst case scenario. What motor parameters are most critical to consider? So that question would actually be a good one for an EasyPower user to email into tech support. For right now, I'm frankly not prepared to talk about it. I think it pertains to your specific environment, and we do have motor authorities that can give you some guidance if you want an email tech support at easypower.com for suggestions on how to start modeling for your particular situation. Frankly, sending us a file and using that as a reference point or a context for your question is also a good place to start. All right, appreciate everybody for attending, and we'll talk to you next week. Have a good one.